Sorry, just a second. Let's see commits. If you just want me to check if you worked like last year.
Yeah, okay. It just started. Yeah. Hello everyone. Welcome. It's our last day after today. I will have taught you all the things. Woo! Yay! Yeah. So we're gonna finish up. We'll do energy. We'll do conservation and momentum, and it'll be great. So a few things to mention. I don't know if I've made my did I mention SPIs to you already? SPI, student perception of instructors.
Oh yeah.
All right, I'll get my shameless appeal. If you haven't done those, remember I appreciate it. It takes like 5 minutes. No, it doesn't even take 5 minutes. It takes like 1 minute. Maybe. Anyway, it takes time. I get that. I remember as a student. I remember every time I opened my ACF being really annoyed by it and just clicking skip every time because I'm like, I just want to register for classes. I don't want to deal with this right now. But if you have a minute to spare, feel free to do during class. I don't care. But I appreciate it. It means a lot to me. It helps me both professionally and also to improve as a teacher. So, anyway, I'm going to keep, I'll send out one more announcement about it sometime closer to when it's done.
When is it due, though?
Does anyone know when the SPS closed? Because that is also a question that was in my mind right now. They opened up, I think, last Sunday or Monday. Okay. Yeah, I think they opened last Sunday, Monday, and they said 14 or 15 days.
Oh, yeah.
So just the safe bet is probably do it by the end of the week.
Okay.
Is kind of the safe bet. Anywho, there is no way for me to tell if you did it. Okay, I can see how many people did it, but again, there's one of those that's completely anonymous, all those things. But yeah, I do read every single, just like the survey I sent out from Test 1, I read every single one. And I do use them as feedback and input to improve. Test 1, after Test 1, I posted the solutions and I started making practice exams. And I started doing that because of feedback and things like that. So I do take it into account. Anyway, there's that. The other thing is that the post-test, that's extra credit. So remember, this is something, it's on a separate web course. I can't even see the other web course. You all are enrolled in some web course named 2053 something assessment, maybe. I don't know the name exactly. If anyone has it open and knows the name, let me know and I'll repeat it. But hopefully the post-test is open right now. I checked with the individual in charge of it, and he said yesterday that he would open it. So hopefully it's open now. Those are also very useful. You can almost view it like a review in some ways for the final. Ideally, that test is a measure of the things that you should know coming out of this class. The way that test is used is every class is given it, so it gives us a standardized way of comparing classes and seeing how people are doing, to see how I'm doing. The reality is we all make different finals, so we can't just compare those, and different grading structures, so we can't just compare grades. So this gives us a standardized measure. Just like you all use the same meter stick to measure stuff, we need a meter stick that's the same size, and so this is our meter stick. Great. So if you do that, remember you get if you just do it, regardless of how you do on the thing, you get that 0.5% extra credit on the final. If you did the pre, you get 0.5% extra credit. Altogether, it's 1%. That is not on the Excel document currently. I probably won't. Just whatever final grade it spits out in the Excel document, add 1. Yeah.
Is it in the same tab? Because if it's in the same tab, it's not open.
It's in a separate web course.
No, yeah, but there was a separate one.
So you're in that web course?
Yeah.
Okay, and there's no post-test currently?
No, there's just a pre-test. It's
okay.
2053 assessments.
Yeah, so I'm going to write on my hand to check in with him again.
Okay.
Because obviously we need to have that done by a week. So I will check in with him. Check. Oh, my pen. All right, while I'm doing this, Sophia can give the joke. I think we forgot last time. Or no, we didn't. Oh.
Unfortunately, I'm way to sit behind.
Oh, it wasn't that bad.
Professor, the physics department. I got
tracker because we started messing up a little, but it was nice because half of it.
Grace that day when I found out it was not.
So it seems like a lot.
Why are you teaching that class?
I know, but still. That's why I'm thinking
Alright.
next or
Like, I
on
think
a
if
spring
you
semester. Also because I got screwed and was 45 on the wait list.
It was like 45 minutes. But
Just
just kidding.
is.
You didn't have to do calculus.
Just keep going.
6:30 is the best time on a clock, hands down.
There's no clock rate. Because
No clock.
the 6:30, both hands are down on the clock. It's good. Huh? Yeah.
But it is.
But everyone's done those clockwise and counterclockwise. All right. My goal is to have a practice test ready for you all tomorrow. Full transparency, the practice exam is just going to be questions from test 1 mixed with questions from test 2 mixed with some new questions for rotational stuff. The problem sets are still very, very useful. Make sure you're actually practicing those and going through those. Also, if you didn't notice, the quiz that was technically due last Saturday, I extended to tomorrow because we didn't finish things in the time frame that I thought we would. So, quiz 9, we're gonna let 10. Quiz 10 is due tomorrow. Quiz 11 is due next Wednesday. Quiz 11, which is your last quiz, it's up there now. It's the last one. It's got everything. It's on moment of inertia and all the things in this slideshow. That one's due next Wednesday. Same thing a little bit later, but make sure you practice these things. Remember, the reason these exist is for you to check if stuff's making sense. That's the reason these 5-question things exist. It's not because I'm out to get you. They're ultimately trying to be for your benefit. Hopefully they work out that way. Yeah.
Where will we find the practice test once you post it?
I'll send out an announcement. It'll be in the files tab. So yeah, like with all the previous tests, anything you need for test 1 will be in test 1. Anything you need for test 2 will be test 2. Anything for the final, there should be a folder called final, and I'll put it in there. Yeah. Any document will always be in that file structure because I just find that nice and organized for me. All right. Good question. So moment of inertia. We talked about it. What's easier, arms out or arms in to spin? Arms in. Why? Yeah, the closer stuff is to the center, the easier things spin. Honestly, if you all can just remember that, that's a really useful thing just to remember moving forward conceptually. That's like this entire PowerPoint is just utilizing that. But if you can just understand that one concept, you'll then actually remember it. And now anytime you see something spinning, you'll keep that in mind. Anything that's spinning that's really far away is actually really hard to kind of keep there. It's really hard to kind of get it going really fast, and there's also a lot of forces involved, that V squared over R, all that jazz. So, just kind of a really interesting thing. What object, what shape is the hardest to get spin? Given the same mass and the same radius, which one is the hardest to get spinning fast? What kind of geometry? A hoop. Because it's literally all of it's on the, assuming the same mass, assuming the same radius, literally all of it's on the outside. And then another quick review question. If I have a kid on a spinning disc, what do we treat the kid as? What do we treat their quote unquote shape as? The point mass. Remember that, and if you're a point mass, it's just mr squared. So we did a problem with that last time, where we had a kid. There was a kid on here, so you had a disc, and the disc was 1/2 mr squared. Remember, I gave you all a big list of these things. When you have just a kid or an object that's spinning at some distance, say you have something on a rope that's just spinning in a circle, that object we just treat like a dot. We call that a point mass, mr squared. That's also, I guess, the worst case is you have all the mass on some mr squared. Anyway.
Are we going to write down any of the point mass or any of that?
No. On the exam, I will give you all a big list in the formula sheet. I'll give you I point mass, mr squared. I disc, 1/2 mr squared. I solid sphere, 2/5 mr squared. It's a great question. Yeah, so on the formula sheet will be a big list of a bunch of I's. And then just depending on the problem, you pick the right one or ones if there's multiple. All right. Yeah, good question. So, we talked about rotational kinetic energy. It's just 1/2 mv squared, but with an I and a W instead. And I think that's literally where we left things. So, great. Two spheres of the same mass are rotating at the same angular velocity. One sphere has sphere 1 has half the radius of sphere 2. How do the rotational kinetic energies compare? So is the rotational kinetic energy of object 1 1/4 that of 2? Is it 1/2 that of 2? Is it 2 times that of 2? Or is it 4 times? Sphere 1 has half the radius. So what happens to my rotational kinetic energy basically if I half the radius? That's the question. And we have the same angular velocity.
The M cancels out because it's the same mass.
I want to just shoot from the hip and say it's a square. I feel like it's square. That feels right.
Yeah, so what's the equation for kinetic energy?
Oh.
With math.
Oh no, I think you're right.
It's,
One half IW.
I.
Yeah, good. Yeah, so then you just chuck in the I.
Yeah.
And then you just make your changes. Whatever changes, put that coefficient in front of that term.
So that would be one for. This is me, sorry.
Yeah, no. No, go for it. Yeah. You're right.
It's too early to think.
It's too early. No, that's totally not true. At 2 a.m., it's way too early to think.
I think I do better at 2 a.m. than 7.
No. Oh,
7
gosh.
a.m.
Is it?
Huh?
What variable is changing? So you said.
The radius is changing half,
Mm-hmm.
and it's squared.
And it's squared, so you square the 1/2.
Yeah, which is 1/4.
Does anything else get changed?
Oh no, because they're both spheres.
Yep.
Okay.
So the coefficients are the same. Omega is the same. So nothing really changed. Like the only thing that changed, yeah.
Patrick Bateman. Oh, okay. Don't do like that. This is how you do it. Don't do like this.
What part?
I'm gonna do the same thing. Who's been indoctrinated?
What's the regular kinetic?
You need to spend some time down the street. You're going to drive safe real fast.
1/2.
There's always you can see a new one.
I know.
Wait, what happened?
It's not like they're getting two more active files.
So if you remember the regular kinetic energy, you just that's how I remember it. Yeah. That does take a little bit of time to learn how to do. The nice thing is that W kind of looks like a V, it's just two of them. I don't know if that's helpful. A looks like alpha. I doesn't look anything like that. There's no like
Really? Football?
that's not
That's more accurate.
She's a Jew.
Oh, sure. So we're comparing the kinetic energy of these two spheres. They're both spheres. Same angular velocity.
That's funny.
One has the first one has
And
half
as
the
we go
radius.
to the stupid Stonehenge over there.
Yes, I remember that.
You see Stonehenge?
Well, what's our
By like
just
garage
to-
beat or something.
Yeah.
what's our equation for kinetic? So
Good job.
yeah, we're gonna do these first steps earlier. What's our rotation?
I don't know.
Like I'm referring to seeing the name.
Yeah.
No, dude, I thought that was like the.
Everybody said that it was gonna be fully.
I don't remember there being more than 4 houses.
Yes, it does. That'd be
That's the
awesome.
new one.
I did. And
And then yeah, what other
I'd also rather have them
houses?
and not leave them.
So what happened on this phone?
Yes.
Or what's
I'm
happening?
not gonna argue.
Harry Potter.
So
Like
they're
they're
basically if I double R,
Four guys all down.
No, the guy who said snake died.
Oh yeah.
Alan Rickman.
So my original
Wait, what? Exactly.
One
Why are
squared
they
is
rate changing every single
double
character?
it.
That's
Two squared is
They didn't even try.
whatever happened better.
Dude,
Alright. Give y'all like 10 more seconds.
that's literally the whole part.
I think that's pretty good. Alright, we'll close this one out in 5, 4, 3, 2, 1. Super slow counting. Alright. So, it's the classic. It's every time I do these problems, you say, alright, what do we care about? Kinetic energy due to rotation. And we got a nice equation for that. And then we need to write it in terms of the variables we have. So here it says I half the radius, but there's no radius. But I's in terms of I has an R in it, so we better chuck that in there. So for this, it's 2 pi mr squared, omega squared. So this is the original. This is like the nothing's changed. Given an M, given an R, given a W, chuck them in there, get an answer. The new one, you make the change. So y'all tell me what changed. Did my mass change? Nope. Still M. Did my radius change? How much? How much did my radius change by? Yeah, so is it half as... And we're writing this one R1. So is R1 half the radius or double the radius? So we're going to chuck a half. And this is where you got to be careful. Whatever happens to radius, you better square it. That's really the only mistake that people tend to make on these ones. If you didn't square what happens to it, you're going to get the wrong answer. It's really easy to prove that. If my radius was 1, 1 squared is 1. If my radius is 2, 2 squared is 4. 4 is not 2 times bigger. So if you just make up numbers, it's easy to see that. Anywho, this looks like a mess, but you just pull out the only thing that changed. You pull out the only thing that changed, which is that 1/4. 1/2 squared is 1/4. And you're left with everything else, which is our original. I know it looks messy, but all you need to remember is that this is the original. Or I say the original. This is the other one. So the answer is it's 1/4. I think the benefit of this setup is this might have been easy to do without like writing it all out. But if I told you the mass was 3 times bigger, and my angular velocity is 4 times bigger, and if I change all of them, this lets you do it so easy. And doing that in your head would be absolutely awful if I changed more than one variable in some weird way. All right. I have the utmost confidence. Oh, yeah, I'll leave it there. Yeah. What's up?
For the last one, why wouldn't it be the 1/2 on the side of R1? So it would be D.
Oh, why wouldn't it be D? So here sphere 1 has half the radius. So here I'm writing R1 in terms of R2.
So wouldn't it be wouldn't the 1/4 be on the 1?
Yeah, so yeah, it's a good question. So is it 4 times bigger or 1/4? If I have half the radius, does that make my eye smaller or bigger? So if R goes down, my eye goes down. Yeah, and so the key here, so object 1 is going to have a smaller energy because all of it's a little closer to the radius. Whereas if you had a bigger object, you're going to have more energy stored in it because like we said at the beginning, the farther away your mass is, the harder it is to spin. But if they're spinning at the same rate, then that one's going to have more energy. Yeah, but ultimately it comes down, this one I put R1. I kind of did it backwards the way I usually do. Usually I say how does object 2 compare to object 1. This one I said how does object 1 compare to object 2. Generally for these, I tend to present it in a form that you don't need to flip things backwards. If I say R1 has half the radius of R2, you don't need to then flip it to the other side. Yeah, that's a good question. All right. A neutron star, and Peter will be able to tell us whether these numbers are reasonable. Of mass, 2 times 10 to the 30 kilograms, and radius 10 kilometers, rotates with a period of 0.02 seconds. What is its rotational kinetic energy? And this is where if you don't know what a neutron star is, I'll let Peter explain it because I think he'll know more than me. How do you feel about neutron stars? Great. Here you go. This is just a fun physics facts.
So, I assume you guys all know what a black hole is. When a giant star runs out of fuel and goes supernova, if you don't have quite enough mass to get a black hole, you'll instead get a neutron star, which is what happens when there's no pressure from the fusion holding it up, but there's enough pressure from gravity crushing it down that you wind up squashing the electrons into the nucleus of the atoms. And so the electrons fuse with a proton to make neutrons, and you just have this giant blob of neutrons floating in space.
And
And
that's
they're-
a star. Why?
That's a good question.
Because it used to be a star. It's a stellar remnant.
Yeah, that's a great question.
Yeah, and so
Does it give off light?
yeah, because they're usually pretty hot.
Not as much as like,
Not as much as like a star that's doing active fusion, but
but they're nuts. Like, look at this mass. This mass, to give you all a frame of reference, I think the mass of the Earth is to 24.
about
This is 1,000,000 times more mass than the Earth, and it has a radius of 10 kilometers. So it's like the size of New York City with 1,000,000 times more mass than Earth does.
neutron star material is some of the densest stuff in the universe.
Yeah.
It is the densest thing that's not a black hole.
But just kind of fun things. Yeah, there's some funky things I think these do. I think they like, is their surface is like the smoothest surface in the universe as well because it's so squashed. I think it might have does it emit things because it spins and little bumps on it?
So yeah, if there's like a tiny bump, it'll like flatten out and you'll get a starquake.
Okay. But yeah, these things rotate super quick. So this thing has 1,000,000 times more mass than the Earth, and it rotates a full time every 0.02 seconds. Like, you can imagine how quick that thing is spinning. Something 10 kilometers every second. Every second, it makes 50 rotations. So something the size of New York City rotating 50 times in...
You could argue that's on the slow end for.
Oh, great. It's on the slow end, too. Yeah. Anyway,
There are millisecond pulsars.
if you look at the answer, so you're all going to do the math. It's got a stupid amount of rotational energy because it's got a stupid amount of mass and it's rotating ridiculously fast. Anyway, so try it out. See if y'all can solve this. There's like 2 steps you got to do. I have the utmost confidence in you. Yeah. Oh, yeah. I assume you already converted.
Yeah, I mean, like, you get period, so I just feel like I used to be the angular velocity, 2 pi divided by 1/3 of the angular velocity, and then work from there.
Yeah, something discipline I realized for you.
The mass is also just a hair lower than it should be too.
To actually be on the head.
Yeah.
I could tell. It seems like there's barely any rotation, which is not something I realized going into this course.
You know, I don't have the study I have on it's a lot of rotational.
Yeah.
Obviously, there's fluids.
Yeah.
I know you get that.
Yeah.
And I've seen some kinetics a lot.
Really?
That's fair.
Oh, it's radius times.
Really? Mostly there's not that much in it. Wow.
There was I mean, I recently took a practice exam for the LAMC, and if I can remember from the physics, I have to remember because I got like a 504.
Yes.
I think it's just the radius times.
I didn't remember the times, so I
I've gotten a couple books, and if I teach these classes, yeah, it's one of those good argument made that we should swap out circular electric with thermodynamics.
Change
Yeah,
it.
there was
Change an angle.
So it's something
Definitely that's what I'm trying to remember. Also, so 2 pi over 0.027.
It's not covered in any course that we currently like. It's not even in the course catalog for any of our courses, which is fun. Yeah, and this one, if you look at the course catalog description, and this is the Florida course catalog description, so used by all the public universities here for this class. Thermodynamics isn't listed, and it's not listed in physics too. But I'm pretty sure it's not
No,
listed in
it's
physics
like
too.
change
Oh my God.
Yeah, it does mention waves, and so that one's.
It does like one full thing.
Yeah, so if you haven't realized, pretty much the only, in my opinion, challenge to this problem is how to get angular velocity. If you haven't realized that you need angular velocity, think through that. But I believe in you. I believe in your abilities to find it. Thank you. What? Yeah, about one of those Kaplan is they're too big. Massive buildings.
Just talking about like, oh wait, no, I didn't.
Radius for the eye. Great.
I'm gonna assume the moment of
How do we do that?
and when I'm wrong,
Specific to this object.
I'm gonna assume the moment of inertia is point mass.
What's the shape of this object? So one mass.
It's the sphere one, the one we just looked at the last one.
stars are?
How would you describe
They're star shaped. No, it's this one. Solid, it's
Solid or
about the
hollow?
diameter. No, it's not.
It's a heater. So we're super easy to calculate.
Because that is the most even distribution of masses, as much of it as close to the center as possible.
Every
If they
second.
it's big enough,
That's what
it's big enough, it gets pulled back out and flattened out again.
Yeah, and that's
Have you ever looked at a picture of like Pluto, Pluto's moon?
No,
They're not quite.
yeah, they like sort of egg-shaped
Yeah.
each other.
Technically, so is the Earth, just not by
And if you look at if you look at how many of that one spins fast enough, then it's really pancake.
radius divided by the time is confusing the regular well, kind of sort of regular velocity. So you're looking for angular velocity. What's the definition? What is angular velocity?
Oh, I don't.
It can be, you can't do that. So regular velocity is meters per second. What's angular velocity?
No, I use math to
Yeah. Degrees per second. We know the time for one full revolution. No, what's the angle you go in one full revolution? So you know how to express it. You just go with math expression. The angular velocity is 2 pi over, and you map the time for one full revolution. 2 pi over capital T. And I think that might be in the formula sheet. I don't remember.
Hey, I got the answer.
Look, So again, this is one of those where like, what are you even solving for? That gives you a sense of what you need. That's why we've been shifting to this instead of just writing our big old blob of givens and then going from there. We start to actually think of what are we even trying to do? What do we need to accomplish that? And then do we have those things? And if not, how can we maybe find those things? So it's 1 pi omega squared. Let's go in order. What's our object here? What's its geometry? I didn't specify it here because I think this is something it's a good exercise. But on the test, I would tell you the shape. It's a sphere. This big old star, like every star. Solid sphere or hollow sphere? Solid. It's a solid sphere. And if you however you find it, it's listed in a few places. It's 2/5 mr squared. Easy. I gave you, and look, I got m in the problem, I got r. How nice. How am I going to find w? How am I going to find angular velocity? What's the definition of angular velocity? What is angular velocity? What's the units of it?
No, radians per second.
Radian, it's angle per time. Oh, look, I have a time in my problem. What does that time represent? One full revolution. So if I know the time for one full revolution, what's the angle? So remember the base definition of this is change in angle over change in time. You all know the angle for one full revolution. You all know the time for one full revolution. And then it's just, easy peasy after this. 2 pi over t. Is this in the formula sheet? I honestly don't remember. No. All right, feel free if you want to put that. I don't know, did I put change in angle over change in time in it? I don't know if I have that on there either. Anyway, it's a definition of what it is. But if you're like, man, I'd really like to know that, chuck it on your note card. So this is my mass, this is my radius, though we need to convert it because we don't forget to do that. And this is we call it the period. So that's just a vocab word that means the time it takes for one full revolution. It kind of works. It's like the period of time for one full revolution. I don't know. Somehow that works for me. So now you got choices. You can like solve for each of these individually and then chuck them in. I'm going to do it the way that I like to do things, which is I put everything in one big equation. And while it looks messy, it's so much easier for me to work with because I just plug everything in my calculator in one go instead of plugging it in 3 different times. And don't forget to square omega. I almost forgot to do that. All I did was chucked each equation into its respective location. And now instead of having to hit enter 3 times in my calculator, and it's so easy to accidentally hit the wrong button somewhere, if you do it one big expression, you can just plug it in as one big expression, and then you can check that what you typed in your calculator is what you wrote down. And that's just such a great strategy for making sure you don't make a silly math error. You are a human being. It is really useful to have strategies that avoid common human errors. And one of those is making a big old expression and hitting enter on your calculator a single time instead of 3 times. All right, and you plug all that in, and fingers crossed it should come out to something like the answer. This number is so big it doesn't even have a name for it. I mean, maybe it does. I don't know what it is. It's literally 3, and then move that decimal 42 times to the right. Like that's, if I tried to fit it on this paper, it'd be hard to fit. It's so big. Yeah. When you start working with stuff in space, you get to silly numbers. Things are big.
I checked, and anywhere from seconds to milliseconds would be a reasonable rotation period. The mass would be more like 2.743 times 10 to the 30.
Nice. So it says very reasonable numbers. Yep. But they're so big that no one's minds in this room can comprehend how big this number is. The universe is so big, just like you all can't understand how many millimeters it is to your house or how many inches it is to your house, like that. Just conceiving of that is just not possible. Brains have limitations. We can only imagine numbers so big or so small, and that's why we do unit conversions to actually move them to things that we can understand. Kilometers. When you start working at this scale, gosh, I don't even know if they have it. When we work with distances, we have like light years. When things get really far, we can break it into light years because that's units we can kind of understand. I have no idea when it comes to energy if there's like some big old unit.
So for energy, I'm not sure there is one, but for mass, we usually work in multiples of Earth, Jupiter, or the Sun.
There you go.
So this would be, I think, somewhere between 1 and 3 solar masses.
Yeah, fun facts.
On the exam, so like here we use the solid sphere one.
Yep.
Will there be a correct answer choice if we solved it during point mass to kind
Yep.
of W off?
100%. Yeah, so yeah, it's a great question. The question was, if this was a question on the exam, would there be an answer that would correspond to different geometries? Whether that's like a point mass or a cylinder, 100%. So when it comes to multiple choice questions, there is a right answer. And then the other answers aren't just random numbers. They're numbers you can get if you do it the wrong way. And that's how you design a good multiple choice test. They're called distractors is the fancy pedagogical name for them. But basically, if you do it the wrong way, you will get this answer. And it's so that you don't just, you can't just use the answers to determine. It can't just be, oh, my number doesn't match that, therefore I did it wrong. Your number could match something if you did it the wrong way. So, yeah, things to be careful of. And that's why when you go back through your test, you don't necessarily redo all the math to check your work. You think through, does my logic make sense? Did I use the right process? And that's a quicker check than plugging everything back in. All right, so conservation of energy, exact same process before. Look, there's our big old list of energies that we talked about before. Kinetic, potential due to gravity, potential due to spring. Now you just have a new one to chuck on. That's it. and then you ask yourself if there's work being done. I'll be honest, I guess I could have a work. No, there is one's work. Does this one have work? Yeah, this one does. Great. So try it. I mean, it's not a new. I would not even call this a new skill. It's literally doing conservation of energy just with a new term on it. The only thing that I'll give you a hint on, the only thing that's like maybe that you got to be careful of. Do you remember how to go from tangential velocity to angular velocity? That's the thing that.
Is it? Yes. Or was it dividing?
So to go from angular to linear, you multiply by r. So if you want to do the opposite. Yeah. So yeah, this problem, the only skill that's going to kind of come up is, do you remember how to go from tangential to linear? Sorry. Tangential to angular. Remember, tangential is just the regular old velocity, v. Tangential velocity, just pretend like it's v. It is v. Do you remember how to go from regular velocity to angular velocity? Check your all's formula sheet. Check those things. It's a really easy way. To do it.
Is there a new variable for is it VT?
Tangential velocity, basically pretend like a string.
But in the formula sheet, is it VT?
It does show up there. There's a couple times it shows up as VT. But it also is V. But VT and V, basically, yeah.
So if you're rolling without slipping, your tangential velocity and your forward velocity are the same.
And we're never gonna do a problem where you're slipping, because that's
So
complicated.
much harder.
Yeah. Gosh, I don't even you'd have to know so. I don't even know.
You need like all the coefficients of friction.
Oh yeah.
Slide
all the questions I had that are physics, a lot of them I took.
Yeah.
So this one fluids, so
Yeah,
like
and it's all really conceptual, right?
yeah, this one fluids. This one
That's chemistry, but also
like
gross.
there's
Physics?
you know, like
Oh no, it's okay.
I'm also like also why I like physics.
You get to
Yeah.
I don't know. There's some part of physics.
Yeah, this is another. I sort of like physics, so
Sure, no, you're good.
this is nuclear force.
Yeah, that's
Yeah,
so that made me figure it out.
Yeah. Oh my god. Okay.
And then.
Oh,
so
great!
this-
It's like the
that-
same problem I gave you on the test.
Yeah, this is flow rate. So I was like, okay, I know this. This one. It was the pulleys. I was just like.
So it seems like so pulleys do come into play.
This was electrical.
Yeah.
And
So
then here's like this one.
oh, interesting. So they definitely emphasize different.
Yeah, it's the last question I had was about like work. And I had this like the area.
Yeah, that's something I haven't quite taught. I didn't quite mention, but yeah, it is just the area. Which makes sense. If it's forced temperature, it's like these two sides or something.
Yeah.
With a ball, it always finishes swimming, so there's no potential.
We're gonna. It says it's rolling.
Oh,
If it's,
Yeah.
yeah. If you have an object that seems like it's spinning, if I say ball or cylinder or generally they'll all say something about it's rolling to let you know it is spinning. But yeah. If there's no friction, technically it wouldn't need to be.
Probably more physics gain energy.
What?
I don't know. I got it to like I got it to 50 something.
Oh my gosh, I didn't see it written out. There's no way to look at all this nonsense and figure that out.
I added gravity potential.
Okay. Wait, what energies do you start with? What energies do you end with? Let me see your big old list.
This I start with 80 joules.
Why? What energy? What types of energy?
Rotational energy.
Anything else? Nothing else? It's not moving?
Oh, do I have to convert that to linear?
Is it moving?
It is.
So it's like I can all the same rules. All the same rules apply.
I thought I caught you with the gravity. I forgot about that one.
So go through your checklist. What energies do I start with? What energies do I end with?
If it was angular, it would say angular.
Wait, are we assuming no friction?
What's cool is you don't care.
Okay.
There could be.
Check the
What are you solving for in this
meters per
problem?
second. It's linear.
You're right.
Per second.
Energy. What?
Lost.
What is the term for the energy you gain or lose?
Maybe radians.
Yeah, and so I didn't specify where that energy was lost to.
Radians are technically
For something to roll, there technically has to be friction. Now, in this problem, it's not going to lose any energy to that, as weird as that sounds. An object that's rolling perfectly, friction actually doesn't. That's the reason we like rolling objects. If you have an object that's rolling perfectly, friction actually doesn't. Friction only affects things that slide. That like.
Because you can't get a grip on it?
So it needs you actually need friction to roll. I mean, think of an object rolling, or think of your wheels in your car. If there's no friction, your wheel is just going to spin in place and not go anywhere. If you're on ice and you try to drive your car, you're not going anywhere. The only reason you move forward is when the tire tries to move backwards, the ground pushes the car forward. So there is friction here for us to roll, but it's actually not what's causing us to lose energy. That's why we like rolling objects. In the real world, there's friction, but if you have something rolling, if it perfectly rolls, like a ball bearing, you basically don't lose any energy to friction. Because it's not sliding. A wheel ideally never slides. And there is some cases to be with that. Yeah.
Mm-hmm. 2mr squared.
And it seems worse than it is. It's gonna look like a big equation, but it's not. It's straightforward though. And the math isn't anything too crazy. Yeah. So it's a simple problem. It just looks like a long equation. I'd say it's straightforward. I'd put this as simple. There's not many steps you got to do. It's just a big equation.
It's just a big equation, which
Yeah.
means there's multiple steps.
But the math is all like nothing crazy. I don't know. I'm biased towards energy. I like energy a lot. All right. What are you even solving for? If you don't know that, you can't solve the problem.
Omega. And then you're looking for how much
Okay.
energy is lost.
Yeah. So what's the variable for energy lost? Work. You are solving for work. If you don't realize that energy lost is work, that's going to have a bunch of problems. There's going to be a few problems on the. I don't know how many. 2, maybe 3. I don't know. It's an important idea that you know that work is energy lost or gained. Is this going to be negative or positive?
Losing energy.
It's going to be negative. Now notice my answer I put as positive because I specified lost, but like when you do the math, you're going to spit out negative. I'm not going to be mean like that in the test. I would just say what's the work done or something. All right. So if you're talking about work, remember there's really only 3 ways to do work. Power equals work over time, which means I need power. Do you all see anything about watts in this problem? No, we're not going to do that. The other way to do work, you all tell me what's the other way to do work that we're not going to use? What are the equations for work that we're not going to actually use it? FD cosine theta. Do you all know the force that's causing us to lose energy? Is it specified anywhere in this problem why we're losing energy? No. Yeah, it's very likely air resistance. Yeah, gosh, if you know how to calculate the force due to air resistance in this problem, you know you're better than me at this stuff. So we're not going to use that. What we are going to use is sum of energy initial plus work equals sum of energy final. The classic, the bread and butter. You got something moving, it goes up a hill, it does things, we can do energy. And then you just go through your checklist, y'all. We got 4 energies to check. So, let's go. Is it moving? Let's say to begin with. We're looking at the beginning. Is it moving to begin with? Yep, it's got, what kind of energy does it have? It's got kinetic, 1/2 mv initial squared. Great. Where do you all want 0 to be? Y equals 0. This is always a judgment call you gotta make. Where it starts. What makes our life really easy, right? So just to draw a picture, if y'all don't know what's going on here, you got a ball that's rolling, and at the top it's also rolling. Yeah, so we're gonna say where it starts is Y equals 0. If you don't make that decision, you might run into problems. Anyway, long story short, where I start, am I above or below 0? Or at 0? At 0. Do I have gravitational potential energy? No. Nope. Any springs? Nope. Am I rolling? You're rolling. So we got to consider that term. That's the new thing. Yay. Great. All right. Then this work. At the end, am I moving? Am I moving at the end?
Yes.
Yeah, great. Am I above or below 0?
Yes.
Yeah. You can see in my picture I went up. Is there a spring? Nope. Am I rolling?
Yes.
Yep. And if you all look at this, it looks like, oh my gosh, but it's just chucking numbers. Solve for things. There's no crazy algebra. I got M. I've got my radius. So if I just go to this problem, I've got M, I've got R, I've got V initial, I've got Y final, I've got V final. Do I have any omegas anywhere in this problem? Do I have angular velocity anywhere in here? No. So this is, how do I find it?
Take the tangential velocity divided by the radius.
If you all remember to go from linear or angular to linear, multiply by R. That's just like the rule, angular to linear. I remember that one. And then, but we want W, so just rearrange it. And this is on your formula sheet. If I give you linear of anything, you can go to angular by dividing by R. If I give you angular anything, you can go to linear by multiplying by R. And there you go. You just do math and you get the answer. At this point, it's just plugging in numbers and solving for W. And this is like the worst case I can give you for this stuff. It's
Good job, spring.
I could have this thing compressed on a spring. Yeah.
Is this like level of difficulty 1 or is it not sure yet?
Yeah, this could be something like this. It seems a little lengthy, but the reality is because there's no free response.
You have to have something.
Yeah. I will need to have some. I say need to. Yeah, I will have some question with conservation of energy with a rolling object.
Okay.
I can almost guarantee there will be one question about conservation of energy with a rolling object.
Okay.
Maybe there's no work done though.
Okay.
Maybe I make it start at rest just to make it a little.
Less time to like.
Yeah. Make 1 or 2 of these terms go away. Maybe I make it start and end at the same height.
Okay.
Sounds like you're going to get right.
Oh, I forgot to ask for this. It should be quick to get them, hopefully. The bicycle wheel, I love bicycle wheel. Yeah. I'm like, we should have used the spinning stools, so we shouldn't need their stool, but we want to grab that as well. If it's easy enough, I should have asked him in advance, but I forgot. Yeah, sure. Now or later, it's like up to you. I can go later if you prefer.
Like, what was the actual?
Oh yeah, it's a good point.
You just do one on the wrong side. We can't do negatives. I think that's it.
Just because this is something I don't have, it's a Thursday. I'm looking up the date of your all's final. I'm fairly confident. So I think you all know this at this point. If you want to know the final for any course, you just Google UCF final exam. Takes you to this website. You put in your meeting pattern. So our class is Tuesday, Thursday, 8 a.m. to 10:50 p.m. Or 8 p.m. 10:50 a.m. Just a reminder, if you don't have this in your calendar, please add it to your calendar. Just don't forget, we start an hour earlier. I will probably send an announcement reminding people. So on the day of the final, it is 7 a.m. to 9:50 a.m. If you show up at 8 o'clock, there is not much I can do. So just be careful on that. I know these things trip people up, but that's where calendars, set an alarm, do whatever the heck you got to do to remember this. I have it on my calendar already. I will be here. Oh, sure. Did you have a question about this or the problem?
It might be. Let me check it one more time to make sure. But I might have a final.
Okay, that shouldn't happen, but if that does, let me know. Yeah, UCF, so the reason UCF generates this really complicated, this thing, is you all have classes that don't meet for 2 hours and 50 minutes. And so UCF does this big old optimization thing. All final exams are 2 hours and 50 minutes. So the reason ours is shifted forward is to make room for other exams that had to be longer, classes and things like that. So there should be no conflicts. They generally do a very good job of that. You have a chance of having multiple exams on the same day. That's something they try to avoid. There's a lot of optimization they do for this. It's a fun little problem to try to solve.
No, it's just I was supposed to have my Organic 2 final on Saturday.
Okay.
The SAS quiz.
Oh, okay. Yeah, so in case like that, yeah, I can work with you to figure that out. But yeah, there shouldn't be any conflicts. Anyway, for this problem, let's just chuck in numbers. So 1/2 times 4 times 10 squared plus 1/2, and I'm going to need more space. Oh, we need the I first. It's a solid object. It's a solid ball. What's my I equation? 2/5 mr squared. So yeah, it's going to be 1/2 times 4 times 10 squared plus 1/2 times 2/5 times 4 times R 0.1 squared times omega, which is going to be that 10 over 0.1 squared plus W. There is no chance I'm fitting this on one line. But I'll do my best. I'll shift things over. Equals 1/2 times 4 times 6 squared plus 4 times positive 9.8 times 3 plus 1/2 times 2/5 times 4 times 0.1 squared. We're getting there. Times, I just got it, well, I think I can fit it there. Times 6 over 0.1 squared. We did it! Well, I mean, I didn't plug it into a calculator. Then you plug it into a calculator, and I think people have gotten the same answer I did. You should get negative 61.6, which means how much energy did you lose? 61.6. The reason I put the answer as positive, here, I'll put it as negative. But if you're describing it that you lost this much energy, we sometimes just put it as a positive because then it's like a double negative situation. How much energy, it's like how much money did you lose? I lost negative $3. The negatives kind of cancel, so you gain 3.
Would that be another thing on the...
No, I'm not going to do anything that mean. No, I'm not going to do anything mean where like the double negatives cancel out and stuff like that. If I put how much energy was lost, I will put all the answers as positive. If I said how much work was done, I would put positives and negatives. Rule of thumb, if I have answers that are both positive and negative, you're probably needing to decide between positives and negatives. If I put them all as positive, I don't care. So generally, that's how I design these problems. If you need to care about positives and negatives, I tend to make different answers positive versus negative. I tend to have an answer, the same number that's positive, and another answer that's negative. Sometimes, though, I'll be tricky, and sometimes I'll have a problem. Say the right answer is 61.6. So again, I'm not going to do like one like this, but let's just take let's say the right answer is negative 3. I might have one answer that's negative 3, another answer that's, so maybe I would do something like this. A would be negative 3, B would be 5. What I don't want people to do is be like, oh, the answer is going to be 5. I just need to decide whether it's positive or negative. So I'll purposely only put the negative 3. I won't put a positive 3 as well. I don't want people to like look at the answers, say, oh, there's only one answer that's the same number. That must be the right number. don't assume, I don't do that for that exact reason. I want people to actually like do the calculations. So, anyway. Alright. I only have one more thing to teach you all. Angular momentum, and it's probably one of like the coolest. So for once, we're actually doing a demo. What's really great is in this room, you all are in spinny chairs. So like we can all do conservation of angular momentum in these spinny chairs, which is great. This is something you all have experienced. But I'm going to show you all something that you may or may, you've probably seen this before. It's like a classic. You can do some wild things with conservation of angular momentum. That's like, how does that work? That seems really weird. And so we'll show those. All right. So before we actually show those things, it's going to show up on the next slide. If P equals mv, what do you think the equation is for angular momentum? Use the magic trick I taught you all. Swap the variable. Angular momentum is L. I haven't, great. P equals L. Do the other swaps. Do the other swaps of variables. We've been doing this the entire time. Let's see if it makes sense to you all. Even though I haven't taught you the equation yet, if you just remember that one simple trick between linear and angular, this will be no problem. Is L equal mw? Does L equal iw? Does L equal iv? Or does L equal mwv? Use the trick. All right, we'll go like 15 more seconds. There's no math here. It's just... Have I conveyed this idea well enough at this point? All right, 5 more seconds. All right, 5, 4, 3, 2, 1. All right. So what's the trick? How do you go from a linear equation to an angular one? You just swap them out. That's what we've been doing this entire time. So what's the... All right, P is now L. Instead of M, what do we use for rotation? I. Instead of V, what do we use for rotation? Great, there's our answer. You swap them. In an angular, now you could write I in terms of M, you could write W in terms of V, but none of those possible solutions match up with that. So like afterwards, if you want to, you could say, oh, this equals V over R, because angular to linear, that whole thing. But if we just want to like make them look similar, you just swap them out. All right. Angular momentum. It's just like linear momentum. And so linear momentum, my hand-wavy definition was linear momentum was how hard it was to stop a moving object. Angular momentum is how hard it is to stop a spinning object or get it moving. That's my hand-wavy definition. If you have more I, it's harder to stop it / get it going. If you have more W, if it's already spinning fast, it's harder to stop it. Again, hand-wavy definition. The units literally come from the math. The variable is L. Why is it L? I have no idea. Angular momentum, I guess, has an L in it somewhere. All right. And then my question to you all is, how did we use momentum? How do we use momentum? We talked about momentum. Why was it useful? We used it for there's a bunch of problems that we used it for. We're called a special type of problem. Conservation. Remember, momentum was conserved. The momentum you start with, that goes to the momentum you end with. Alright. The same exact thing is true here. The angular momentum you start with is the angular momentum we end with. And so let's go ahead and you all are in spinning chairs. Let's experience this. So L initial equals L final. If you all spin in a chair, how many objects are there? Let's pretend like the chair is not an object in it. Let's keep it simple. Like, pretend like the chair's not. Pretend like you're spinning. You're spinning. Somehow you're a ballerina or ice skate or whatever. You're able to spin on your foot, no friction, all that jazz. How many objects are there? Not a trick question.
You.
One object, right? Just you. We're gonna keep it simple. One object. Great. So just like when we did momentum, if there's 3 objects, add up all their momentums in the beginning. If you have 3 spinning objects, add up all their L's. But if there's only one of them, I1, W1, initial, equals, you start with your arms out, you bring them in. Have I changed how many objects there are? No, still one object. I final, W final. If you only have one object, you're like, but wait, doesn't this mean nothing changes if there's one object and one object? Like, in momentum, we always had collisions. So you had to add like 2 objects at some point. The thing with angular momentum is we don't need 2 objects. Because when we had one object, you didn't really change its mass. It's not like you like chucked a bunch of mass out of it. But if I'm spinning, how can I change my I? Say I have my arms outward. How can I change my moment of inertia, my letter I? You bring it inward. All right, go ahead and do this, y'all. I'm sure you've done this before. You're in spinning chairs. Spin around with your arm in. Yeah. Get some space. We got like a third of the color. There's plenty of room to spin around in chairs. Feel it yourself. Put your arms out, then bring them on in. There's not enough people spinning in this room. Spin around. And then do the opposite. Start with your arms in, and then bring them out. And see if it makes a difference. It's a subtle thing, but you should be able to feel it. If you want to make it more extreme, stick your legs out and then bring those in. Your legs tend to have more mass than your arms do. Stick everything out and then bring it all in. It seems silly, but it does the job. Start with all your mass really far away and then bring it inwards. If you stick your legs out, it makes a pretty significant difference.
You have to start fast enough that you don't lose too much speed.
Yeah, these are not the spinniest of chairs, but they do the job. I am slightly dizzy. I really did. Yeah, but like if you ever try to stick your legs out and bring it, you get spinning much faster.
You said this thing on the baseball or display or like a bigger room, but it's like only like this wide.
Yeah.
Kind of hold it in front, and you just be on that all day. And
Yeah.
that way you can stop yourself with just like leaning out or just jumping off.
Yeah. That's it. So someone mentioned there was like if you ever go to a playground or something, they might have like one of those big old things that spin around in a circle that you can kind of hop on. Ideally, they have guardrails on the outside. Ideally. But like when you all go to the playground, which you're like, why would I go to the playground? At some point, you will probably interact with kids in your life, whether babysitting or your own or whatever. Who knows? Whatever. Pro tip: don't go to a playground without. Well. It's a little funky to go to a playground if you don't have a kid with you. It gets a little as you get older. You are kids at heart. You're not. Yeah. Anywho, if you ever interact with one of these things, test this out. Like, what you can do is the easiest way to get these things spinning really fast. Run on the outside. Get it spinning as fast as you can on the outside. That's where you can apply the most torque. And then move your body towards the inside. The more you move to the middle of that object, it's going to spin faster and faster and faster and faster. It's just, you can experience it for yourself. And this is just conservation of your momentum. If you make I go down, so if this side I goes down, W has to go up. That's what the math tells us. If I goes down, W goes up. You spin faster. Now, there's some weirder kind of other cases of this. So that I'm gonna let Peter demonstrate this one, and you all can try this one if you. Yeah. So he's gonna demonstrate this, and then when we break, you or the student. I don't really care who. We'll do Peter do it first then. Alright, so it's a wheel. It's spinning. Now, something I haven't quite mentioned is angular momentum has a direction. It has the same direction as W. So right now when Peter spins this, let's practice if we know the direction of W. According to pretty much everyone's perspective here, is that clockwise or counterclockwise? Go ahead and do the right hand rule. Which way does angular velocity point? That's the direction of angular momentum. Take your hand, curl your fingers, make sure you're using your right hand.
I don't know if this thing's 100% balanced.
Yeah, it might not be.
Out of the.
Yeah, if you curl your fingers, it's away from it's the spoke here. It points along that spoke. So the direction of angular momentum is that way. It's a vector. It wants to be that way. It wants to stay that way. Conservation of angular momentum is conserved. All right, so now Peter's going to get in a chair. All right, so Peter is going to put his feet on the ground. We're going to do it this way first. We'll do the simple one. Yeah, good luck. All right. What's Peter's angular momentum? Which way is it? Up. Great.
It hasn't started spinning.
It hasn't started spinning yet, and I'm going to try to figure out, I think this will work fine. All right, so Peter's angular momentum, well, actually right now, is anything spinning?
No.
No, so there's no angular momentum. All right, if we spin this thing really, really fast, however we want to get it going, I don't know if I can get it, hopefully I can get it fast enough to show it. All right, which way is that angular momentum? Do the right hand rule.
Down.
Rotate your hands, it's down. All right, now, Peter's going to lift up his feet, and then he's going to flip the whole thing over. What did he start doing when he flipped it over?
Spinning.
He started spinning. Why?
Gyroscopes and stuff.
So, when Peter was spinning it, the wheel had an angular momentum down, right? It was cool with that. It was so happy. When he flipped it, now going. Is that conserved? Something was down and now it's up. Or is up equal down?
No.
So what is his body? Remember, he's like connected to this. To make it conserved, his body has to start turning so that the two arrows cancel and we get the original. It's kind of funky to draw this. So, yeah, to kind of draw this, we're going to pretend like Peter is a cylinder and attached to Peter is another cylinder. So this one was up. This one was up, and now this one's down. How do I make it conserved? Say this was like positive 5. My L here was positive 5. Here my L is negative 5. Positive 5 doesn't equal negative 5. What do I add to negative 5 to make it equal positive 5? 10. So Peter's body better make one that's 10. Because 10 plus negative 5. And how does Peter's body make one that's positive 10? His whole body starts rotating the other way. So it's a really weird thing. There's lots of different examples of this. So, all right. Who wants to spin? Great. Come on over. So there's a couple more of these. And I really highly recommend you all, during the break, try this out. Because you can actually, feel it pull. You can feel it, pulling your body as you rotate the thing. So the other one that we're going to do, go ahead and sit on a chair. Ideally, we'd have chairs that spin better, but I didn't do a good job preparing, so you're getting your crappy ones. All right, hold it like this. All right, to make this a little easier. And the faster I spin this, the more angular momentum. All right, which way is the angular momentum of this wheel?
This way.
That way. What I want you to do is twist it so that the angular momentum, so pick up your feet. All right, now start to twist it, rotate the thing. And his body starts rotating the other way because he's twisted it from that way upwards. And so his body's trying to fight that. And then if you twist it back. It's really weird. It feels like magic. And it feels, again, he can feel, what do you feel when you're doing that?
It's moving me. It's literally moving me.
It's really weird because you're all used to things like pushing you. There's nothing, he's not touching the floor, but it feels like something's pulling your body. The really fun thing with this is how you can make how do you make spacecraft turn in space? There's no walls to push off of. There's no, what if you don't want to keep shooting hot gas out? You only have so much hot gas you can shoot out. They literally just have spinning things in the spacecraft, and if they spin those things up, or if they rotate them, the whole spacecraft will rotate the opposite way to cancel out to make sure angular momentum is conserved. So literally, spacecraft can rotate in space by just having a wheel on it that spins. And you have a bunch of these wheels in 3 different directions. They're called gyroscopes. Yeah, it's really cool. So anywho, we're on the break now. Come experience it. Like, it's fun. I doubt any of you all have a wheel that you can hold the spokes of at home. It's nothing fancy, but try it out. Come experience it. We got like 7-8 minutes. We're just gonna chill. Like, it's break.
Do you want to do it?
Yeah. Do it. It's fun. It's a weird feeling. This is one of like the coolest things because you can like feel it. A lot of things in physics you just see it. Yeah, there you go. It's a funky experience. All right. Look, you don't even have to change. Yeah, there you go. I'll spin.
Put it higher.
There you go. Maddie, you can spin it for her. You just smack it a bunch of times. The faster you get it, the better it gets. And this wheel has a bunch of mass on the outside just to make eye bigger, but you all can do it. Yeah. And just rotate it around. Just like feel it. Experience. Do you feel it pulling you?
Yeah.
It's a weird, and again, these chairs aren't like super frictionless, so you lose some
It
energy.
feels like it's like wind.
Yeah.
Like, is it like some type of wind?
There's wind from the spokes behind the fan shape, but that's not what's doing it.
Oh, okay.
No, it's literally your body just counteracting the force. For
But
you to
you also
turn,
feel it resisting when you try and pull it into
Oh,
the direction, right?
and some of what's happening here is you're like
That's like-
applying a force and it's applying a force back. So it all does come back to Newton's third law, but it's a little tricky to show. But this is like a classic. You go to like a science center or something, they have this.
You gotta get a big one.
Yeah.
Probably feel it resisting.
Huh? Oh yeah, yeah. If you get it spinning really fast, you really get the experience of this. Yeah, and I'm trying to think of if there's ways you can experience this as well. This does slightly explain why bikes balance so well. Bikes, though, most of the reason your bike stays up when you're bicycling is not due to the spinning. It's actually due to like the steering. There's a really good YouTube video where someone basically made the steering do the opposite, or when they turned left, the bike went right, and they kept crashing because it's a lot of the reason you stay up on a bike is like when you do that. Try it out, Yanni.
Yeah, let's pull a big one with it.
Yeah, it's kind of heavy because they want the motor to actually be able to.
Yeah.
Alright, yeah, just rotate it around. It feels really weird. Again, the effect on you is not super big because these chairs are slightly. Yeah, it's fine. That's just the wheels. That's just the wheel spinning. Yeah, it's not the reason that you're actually turning. Yeah, it's a fun thing. So, anyways, I'm just gonna walk around. People are more likely to do stuff if you kind of 5 people right now. So the reason I have snacks on the table. Go in the truck, girl. Yeah, see, great. Let's keep trying. There you go. Alright, because it's closer to your body. Remember, it's easier to spin things in the clothes. Yes, it's what you want it to be. And they also chose a bicycle wheel here because it's like the rig is the worst kit. Like, it's got the most moment of inertia for a given size. Yeah, and this is how spaceships, they literally, now instead of like rotating something, they just have 3 different wheels. And they just spin them up and spin them down as they respond.
For this one, so like,
Right? Yeah, great.
I mean, that like I say, like the free responses aren't horrible, but like it's how you're getting more time consuming, so you feel like.
Yeah, it's weird. It feels magic. That's just like it's. Again, people. There's a reason this is like such a popular demo. It feels like magic. Yeah. It's just whenever I went to TJ Ross or just pick the shirt that has the goofiest, interesting things on it, and this one is one of those. So yeah, it's good. You ready? Yeah, like it's a fun experience. Yeah, it's just a little heavy, so I'm holding it here so it doesn't get through your hand. Don't believe me.
I know, I thought
Yeah, there's a few of these demos that are just like they're not what you expect. I mean, that's a lot of physics demos. That's what we choose generally. It's like, wow. But it does just come down to the angular momentum just doesn't want to change. It's a vector, it doesn't want to change direction. When you make it change direction, it makes something else spin if possible. Yeah.
Because I had a large yesterday.
It's probably just gonna do it. I mean, like all the kids.
Home health aid, so I get home.
Yeah, and so as you rotate your body, you're trying to cancel it out as best it can. And there didn't used when you rotate this way, now there's an angular momentum this way, but there didn't used to be. So how does it cancel it? Your body rotates the other way to try to cancel it out. Your angular momentum in the up-down direction starts at 0, and it wants to stay at 0. Yeah. We got a couple more minutes. I'm gonna keep rotating around. Well, it'll just stay in this room.
It depends what you did.
Yeah, because it's a moment of inertia.
Oh, yeah.
So yeah, your body has a big R square. Will have more. You're like a cylinder. You'll have so the bigger you're in, the less you're gonna rotate. Because it's harder to get your body perfect. Yeah. It's cool though. Alright. Keep on rotating. Experience it. It's more memorable. Like you can watch someone ride a roller coaster and you'd be like, wow, look at him go.
And he's in pain.
Yeah. You just want your feet off. Yeah. Your body won't be able to rotate itself. If there's forces opposing you, no, you're not going
No.
You just want this thing to have the biggest moment of inertia so that, because when you rotate, so right now, there's no angular momentum up down. But when you rotate it, now there is. And so your body needs to generate the exact opposite. Yeah, so the benefit of the hoop is it gives you the bigger eye with less, given the same amount of mass, so notice they literally stick way too. You can't roll very fast. Because you would have to roll it a very far. I can give it a good yank. It's just easier to do. Yeah, I was like, it's just easier to. And then just rotate it. Anything? There you go. You get a little bit there. Here, let's spin and then keep your feet as inwards as possible. There you go. And again, it's not gonna be a huge effect because there's friction that's fighting it. Yeah. And the quicker you kind of rotate, the more jerk you get. Because it's like an instantaneous force that experiences, but then the friction dissipates it, which is why you stop spinning. Otherwise, you keep spinning forever and ever. All right. You all are welcome to keep doing this while I keep going over other things. Yeah, sure. Do you want to? It's fun. All right, just spin it for her while I keep doing things. Yeah. So I'm just gonna keep passing that around. All right. So we can finish the last 5 or 6 PowerPoints. Alright, so we'll just keep going now. A solid sphere, hollow sphere, the same mass and radius, they rotate at the same angular speed. Which one has the higher angular momentum? It's just check. This is like the simple check. Do you understand the equation? Does the solid sphere have a higher hollow sphere? Both the same, possible term.
No, I got it.
No, you're good. No, I was going to say that. Yeah, it's heavy. Well, it's got a lot of mass on it. Alright, there you go.
Angular momentum.
You feel it?
Oh, you're right. Hollow sphere would have a higher.
Yeah, you just got the faster I spin it, the more angular momentum.
Yeah.
But you feel like you have to put a force into it, don't you? Because you're fighting it. It doesn't want that to happen.
Yeah, because the moment of inertia.
You're not changing its gravitational potential energy. You're not fighting that. You're literally fighting that.
So the solid sphere has a higher angle.
Okay, when you hold it like that, you're fighting.
I feel like I just got that in my fight.
It's good for you.
I just remember that for like the angular velocity and stuff.
Alright, who else? You want to try that? Her backpack, you want to spin? Hold it spin. It's memorable. Alright, do you all want to spin?
Wait, the rotating the space.
It's very memorable. Yeah. You're gonna want some space though, so. Alright.
No, let's do the hollow sphere.
You sure?
I think so. I
there's something tugging against you.
Oh yeah, what? Okay.
Yeah.
Same mass and hollow sphere.
And the answer is it's constant advantage. Something is like you're on that force, and this is the opposite force that's fighting.
Yeah, so if they're shooting at the same speed, it has more momentum.
Oh.
It's a fun weird experiment. Alright, 5-10 more seconds for this. It's fairly straightforward.
Oh, what? Sorry, can you do it? I have it back. They're doing renovations right now, so I'm kind of waiting.
Alright, in 5, 4, 3,
Wait, I'm spinning.
3, 2, 1. Oh, yeah. Which of these has a higher angular momentum? Solid sphere or hollow sphere? Same mass, same radius, same angular speed. Do they have the same? Is the solid sphere higher, hollow sphere higher? Impossible to determine. Alright. So, what's the equation for angular momentum? Lil, I don't know. Lil? I don't know, however you want to pronounce that, Lil. Great. Now, here's the problem. It says same mass, same radius. Do they have the same I? No. What's harder? Remember, I represents how easy or difficult it is to spin. What was our rule for determining whether it's easy or difficult to spin? What's pretty much the only thing that matters? Yeah, how close it is to the center. How close the mass is to the center. A hollow sphere has like all the mass on the outside. It's worse. Well, okay, worse, quote unquote. It is harder to get something to that. Long story short, the I for a hollow sphere is bigger. I actually forget the value. Did you all find it? Even if you don't know the number, it's harder because it's on the outside. It is 2/3. Sphere is 2/3 mr squared. For a solid sphere, it's 2/5. Which one's bigger? 2/5 or 2/3? Great, so that one's gonna have a higher. That one's gonna have a higher angular momentum, given the same everything else, given the same m, given the same r, given the same w. If we write these out, L for solid sphere is going to equal 2/5 mr squared omega squared. Not omega squared, just omega. L hollow is going to equal 2/3 mr squared w. Oh, the wrong way. 2/3 is bigger than 2/5. That's it. Alright, I really hope this one goes smooth. If not, I failed. A figure skater is spinning in a circle. If she brings her arms in, what happens to her angular momentum? Does it increase, decrease, or stay the same? Oh, be very careful. What are we solving for here?
Momentum, not speed.
Be very careful.
Her eye changes, but other than the
I'm going to underline this for you all.
conservation momentum.
Oh.
No, just
Sure.
in general.
Yeah.
So what is angular momentum versus speed?
Angular momentum is the L.
Well, okay, yes, but like in like.
Think of it like what's the difference between regular momentum and velocity.
Exactly. I know who you are. So I was just like, figure it out.
So P equals mv.
Yes.
So remember my hand wavy definition for this whole momentum thing? How hard it is to stop it. So just because something's going really fast,
So fly is going really fast. We can stop that.
so easy to stop. Why?
Because it's mass.
Its mass is really low.
Okay.
It's m times v. So not only do you care about how fast you're going, because it's hard to stop fast things, you also care about the mass of something. It's much harder to stop a semi-truck going 5 miles per hour than it is to stop a fly going 100 miles per hour.
But then,
You're one of the rangers
like
holding
apply
the
that to
ball.
this, so we don't have like.
Same exact thing, except instead of m, it's I.
Why are you so evil to
So instead of it being how difficult it is to move something is like its mass, now we have this thing that's angular, a moment of inertia, how the mass is distributed. And the farther away it is, the harder it is to like speed up or slow down.
So the hollow sphere is harder to speed up, which is why it has a higher.
Yeah, if you get it to the same velocity,
Okay.
yeah, just like a truck going 60 versus a fly going 60. They have the exact same velocity,
Okay.
but one's harder to stop because it has more mass. This one's harder to stop because it has more. It's farther away.
Another way I like to think of it is.
All right, 5, 4, 3, 3, 3,
I think I got it. Okay.
3,
I did it.
2, 1.
Okay.
They stay the same. Angular momentum is conserved. Now, I will now give the question that everyone. Well, it's still open, so if you didn't change it, great. Let me give the exact same question, but do the one that you all would prefer. A figure skater is spinning in a circle. She brings her arms in. What happens to her angular velocity? Actually, you know what? Let's make this more interesting. What happens to her moment of inertia?
Well, the radius gets smaller.
Brings her arms in. The speed increases, so her moment of inertia.
Oh, yeah, but also the radius decreases.
So what is moment of inertia? What is it a measure of?
No. If she puts her arms in,
Remember momentum.
Yeah, this is
it's like MRI.
Yeah, so this is an angular
So
velocity.
like, if you think about it, her radius
Angular
gets
velocity
smaller.
goes
yeah, because it has to. They have the moment of inertia is equal to them. So if the one speeding up, getting bigger.
She does.
Yeah.
But her moment of inertia is smaller because her arms are farther in.
Well, I figured out the answer.
Moment of inertia goes down. So I goes down. Because the mass is closer to the velocity. It's much easier to stop something if the mass is really close to here. So they're actually tied together.
Well, exactly, but then it does that. And this.
So what's happening here, and this is the thing that's kind of weird, the velocity is actually the same. You'd be like, what? Kind of sort of the same. If you're spinning in a circle here, my arm here has to go a farther distance in the same amount of time. So it has a certain velocity. When I bring it in, it has a smaller distance to travel. So you're gonna spin faster so that your velocity kind of stays the same. Kind of sort of. Yeah. But it literally just doesn't have to go as far. Yeah. So momentum is still conserved. Momentum is still conserved, but momentum is tricky to work with. In this case, because you're X and Y, and that's a pain what to do. So we work in this, but it is just angular. It is conservation momentum. You travel at a certain velocity here. To bring my hands in, for them to, if I just bring them in, I can hot, right? They slow down. So when we do, we speed up so they have the same velocity. Yeah. So they're all kind of happy. Yeah. This is just another way of looking at it that's way easier mathematically to do. Like if we did momentum, you'd have to do X, Y. It's awful. All right. So if you haven't thought about this, moment of inertia is the mass closer to the center or farther from the center? If she brings them in, closer to the center. If you're closer to the center, then your moment of inertia went down. All right, let's just put this all together. What happens to her angular velocity? And I should probably change the orders of these. But yeah, this is just trying to convey the whole idea of what's going on here. Yeah, these are free points, I guess. What happens to angular velocity? We'll go super quick on this one, like 30 seconds. If we did this, if you're in class, if you're at home and you have a spinning chair, you could do it too. But yeah, the fun thing with this is if you just have a spinning chair, that's all you need to like do these things. You can't do the bike wheel one as much.
My chair would have me fall over.
Yeah.
Unstable.
Yeah, that wouldn't work well. But it's great. Do the playground rides. They're so fun. Like, you can really get those things going. If you run around those things and you hop off and you like move your body to the inside, your mass is so much bigger than all the kids' mass.
You could also spin the swing and then do that too while you're spinning.
The swing.
Like, have you guys ever done the wraparound thing on the swing?
Oh yeah, that's another good one.
Really fast.
Yeah, if you're on a swing, if you bring your mass really close to it, you can really whip yourself. If you're like on a swing, but you like you like twist it up, and then it wants to unravel.
I say you gotta spin it.
No.
You tie it around this anything, right?
All right, 5, 4, 3, 2, 1. Great. Fingers crossed. Yay! It goes up. All we did was so like I should have maybe changed the orders. As L goes down, W goes up, so that they equal the same thing. Conservation of angular momentum. Great news. You all are spared. This is technically a vector, but I'm never going to give you an object where like the axis of rotation is changing. So all you care about is clockwise, counterclockwise. We are going to care about plus and minus. We're going to care which way things are spinning, but they're just going to be either clockwise or counterclockwise. I already did this, so gone. And look, y'all. Do you see what's going on here? These are the last problems we're ever going to do. Like, this is the last practice of new things. And then our entire course, I've taught you all the things that I was supposed to teach you. I didn't teach you thermodynamics, but technically it's not in the course catalog, so. Anyway.
That's what physics 2 is for.
You won't get to thermo there. Alright, a cylinder with rotational inertia I equals 2, I just give you the number, rotates clockwise about a vertical axis with some speed. It's spinning. Spinning clockwise. You got a cylinder, you got something spinning clockwise. A second cylinder with a different moment of inertia spins counterclockwise about the same axis with an angular speed of 8. So you got two cylinders. They're both spinning on the same axis. So like, if you imagine what they're spinning around. But one spinning clockwise and one spinning counterclockwise. And they're separate from each other. I mean, that's the only way they could spin opposite directions. If they were attached together, how would that make sense? Like, you got two different cylinders, they're separated from each other. One spins one way, one spins the other way. But then they couple. Couple is just a fancy word to say they get attached to each other. It's used a lot in like science and engineering. Couple of two things coupled together, that means they're tied together. They're stuck together. If the two cylinders couple so that they're stuck together, what happens? What's my new angular speed of the combo? And then the final question is what percentage of the original kinetic energy is lost? If you're like, what is this? This is how a clutch works. Fun fact. This is how when you change gears, you got a bunch of things spinning, and you need to connect them together, and it is a conservation of angular momentum problem. So in your car transmission, you have different gear sizes and things, and you literally get two spinning things, and they get stuck together. If you've ever done a manual car, that's what the clutch does. The clutch disengages two rotational things. You swap stuff around. Then when you release the clutch, you got to do it very gently. If you release the clutch super quick, you got a spinning thing and a not spinning thing, and they like hit each other really quickly, and that doesn't go too well. It goes quick, like it seizes or something, and like makes your car turn off. Anyhow, most of us don't have to deal with manuals. I barely know how to drive a manual. But it's a fun thing. Anyway. So here's a pretty picture of it. How do I want to draw? One cylinder spinning this way. Another cylinder spinning the other way. So they're like on top of each other, but they're not touching. And then at the end, they're stuck together. And I don't actually know which way they're going to spin, to be honest. I'd have to do the math. All right, so the key here is I've got spinning things, and something changes. Then I say, what's their spinning afterwards? Just like momentum, where you have two objects, and they collide with each other. They get stuck together. What's my final velocity? This is the exact same problem as two objects running into each other. What's my final velocity? Just instead of stuff moving linearly, now they're spinning. Oh, I had my directions backwards, if that matters. It doesn't really matter. I didn't label. At the end, it will spin clockwise. There's just some quick math in my head to figure that out.
Oh no, I'm saying
No, it is.
I'm like confused because we haven't done a problem like this
100%.
yet. So like normally for these types of problems, like I'll try and figure it out and it just doesn't work. But then like the next one, since we already did a practice one, that's like
Totally makes. Yeah, that's why I have two of them.
Yeah.
So the key here is that pretend like this is a momentum problem.
Mm-hmm.
M times V's equals M times V's.
Yeah.
How many objects do I start with?
2.
So how many angular momentums do I start with?
2. And then you end with 1.
And then you end with 1.
Okay. So you just made it worded to confuse us?
No, well, so the wording here, it has to, I have to give these details. I have to say they have the same axis. Okay. So the additional wording is so that you can actually draw the picture correctly.
Okay.
Because if one was spinning like this way and one was spinning this way,
it wouldn't work.
You'd have to do it different. It would actually be different.
Okay.
Yeah. So all this wording is to just get this picture.
Okay.
That's why I made all the picture. Yeah. But yeah, this is just like conservation momentum. Just instead of P's, put L's. How many objects do I start with? How many objects do I end with? Do it like you would do conservation momentum. There you go. Is that this one or? Let's see. Did you do energy? What did you do? Okay, sorry. Okay. So L1 plus L2. So just like momentum. So if we did conservation momentum, we have sum of p's that I start with equals sum of p's I end with. So how many p's do I start with? So I'm gonna add them. Now the thing you gotta be careful of. Remember when we did momentum? If a car was going to the right, is this momentum positive?
Oh, okay. Wait, yes, I remember now.
If a car goes to the left, is the momentum positive or negative? So in these cases, are they both going the same way or opposite? So, and the other thing here to be careful of is direction. Are they both going the same way or are they going opposite ways? Remember momentum, if an object's going to the right, it's positive. If an object's going to the left, it's negative. So we are solving for omega final. And we know this is going to be an angular momentum problem because it's two things that get stuck together. Great. So sum of angular momentums I start with equals sum of momentums I end with. And then again, same like momentum. How many objects do I start with? 2. So L1 initial plus L2 initial. How many objects do I end with? 1. And I mentioned this before, you gotta be careful. Are they both going the same way to begin with or opposite ways to begin with? So decide one of them is positive, decide one of them is negative. I don't care which one you say is positive. I don't care which one you say is negative. Just be consistent. If you decide that clockwise is positive, awesome. your final answer, if you get a positive answer, means it's clockwise. If you get a negative answer, it'll be counterclockwise. So just, you decide. I don't really care here. What I do care about is that you realize that they're not the same direction. So actually, you all tell me, which one do you want to be positive? Do you want the clockwise one to be positive, or do you want the counterclockwise one positive? Great, that works for me. So we're going to make this one positive, and we're going to make this one negative. It does. I'm not going to be picky with this. If you all think of the angular velocity term, you would do like the right-hand rule. So angular velocity for object 1 would be down, and angular velocity for object 2 would be up. But I don't really care. I didn't give you all directions. I didn't tell you what. Well, kind of did, but I didn't tell you if you're looking from above or whatever. So now just how do you calculate L? What's the equation for L? Just like when you all did momentum, what's the equation for P? This is momentum. I'd replace these with these be P's and I'd put MV, MV, MV. Now instead of MV, I have IW, IW, IW. So it's the same skill set. If you can connect those neurons, the neurons that understand momentum, to this, you're going to be good to go. All right.
I don't know how to do the second one, percentage of the original kinetic energy loss.
So it's conservation energy. How much kinetic energy do I start with? How much do I end with?
That's what I was gonna do.
Totally works.
And then I got really confused with, because we don't know mass.
Do you need it?
Well, like it cancels out, and then I tried to do that, and then I got confused on how exactly it cancels out.
Are these objects moving?
Yes.
Like left, right, up, down?
No, but they're spinning.
They are. So their velocity is 0, but their angular velocity.
So do I use
So this is
IW, not
yes.
actual kinetic energy?
Because they're not actually moving. Their overall velocity is 0.
So we can say kinetic energy.
Oh no, you're right.
Spinning.
So when I say kinetic energy, it's going cuts down.
Good.
Yeah. If you're like confused on the second part, when I say original kinetic energy, I'm talking about all the rotational and kinetic. Are these objects actually moving left, right, up, down? No, their kinetic energy, their translational kinetic energy is 0. So if you I'll make this maybe a percentage of the original rotational kinetic energy. There is no translational.
And you add the two
Yeah, perfect.
together,
Yep.
and then
Equals the what? Yeah.
the final.
Or specifically we'll do final minus addition. We're solving for W.
Yeah, okay.
Alright, and then how are you doing on the
I'm just gonna wait for you to explain it.
Okay. That's fine. Alright, so what's the equation for L, y'all? The next step. IW. So I'm going to give myself a bit more Remember, L equals IW. So we just take this. Initial is going to be I1, W1 initial plus I2, W2 initial equals. Now this side, if I have two masses and they got stuck together, I have a 2 kilogram mass and a 5 kilogram mass. If they get stuck together, what's their total mass? If I have a 2 kilogram and a 5 kilogram and they get stuck together, what's their total mass? 2 kilogram, 5 kilogram together is? 7. What crazy math operation did we do there?
Addition.
We do the same thing with eyes.
Oh, cool.
If I have two objects and they get stuck together, what's their total I? Just add them together. Again, all I need to convince you all of is that this is just like regular momentum. It's just I's and W's instead of M's and V's. Oh, I forgot my minus sign. There it is. You just plug in numbers. IW minus the other IW equals all the I's together times W. IW, IW, IW. Purple, purple. So, 2 times 5 minus 1 times 8 equals 2 plus 1 times WF. So you get 2 equals 3 times WF. And we get WF equals 2/3 radians per second. Did we decide clockwise was positive or counterclockwise was positive? This is clockwise because it's positive. If this had come out negative, it'd be counterclockwise based on our deciding. We decided that clockwise was positive. We decided that counter. So this is positive. So this is clockwise. Just like if you all did a momentum problem and you came up with a positive velocity, that's to the right. A negative velocity would be to the left. IWs, 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 just like MVs, 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 MVs. All right. For the second part, what percentage of energy is lost? What's our fancy word for energy lost? You're just solving for W. So I'll set up the second, the last problem together. Well, I'll show you all the last problem. So part B says, how much energy is lost? So part B says find W. Here, I'll copy all this over because I'm going to need it anyway. So part B, I've given you all the hint. We're solving for work. What energies do I start with? What energies do I end with? So this problem is kind of bringing it all together. And again, I know if this seems complicated, seems tricky, once you do a couple of these, if you are cool with momentum, you will be cool with this. It's just doing a couple of these to kind of make those neurons connect and do the same thing. Same process. IWs, IWs, and NVs, NVs. That's right. Part A still or part B?
Let's say spinning.
Yeah,
I
right.
understand the W file and I have the total plan and rotation.
Yeah.
I just don't know where to go from here. Cause like,
So what was that?
B.
Okay.
Because that's 2/3, that's the.
So you got the final kinetic energy. Okay. What energy do I start with? Because we're just doing conservation energy here. In the beginning, what's going on? It's rotating. So what kind of energies do we have? And how many objects do we have? So they each get their own.
Yes.
So in the beginning we have the rotational kinetic energy of 1 plus the rotational kinetic energy of 2.
Yes. And I got that 67.
Alright, so that's my original. Is there any translational velocity? Are these cylinders like moving left, right? So there's no squares. Are they? Okay, technically when they couple, they're square. We're gonna pretend like their height's not changing really to make things more easier. So no gravitational springs.
Yeah.
Okay, so just build conservation energy. Energy initial, you got it. Plus work equals. What energy do I end with?
Energy final.
What kind of energy final? What energy? Yeah, what?
Rotational stuff, it's the.
Yeah, so it's just 1/2 I. So we use the total I. Because how many objects do we have at the end?
So.
We used to have 2.
No, we still have 1.
We have 1. which has some I, that's a combo of 2. And 1/2 I omega squared.
Sorry, you've lost the numbers
It's the
somehow.
exact same thing we did with the initial.
Oh, really?
Just do it for the, just the end.
Okay.
Instead of 2 objects, now I have just 1 object, an I. That's I1 plus I2. And an O.
And that's equal to what?
So energy initial plus 1 equals energy final.
Yes.
Solve for W.
Hold on, what was your starting number?
Energy final is them both together. So that's gonna be
1/2 I omega squared.
Sigma chi's gone.
omega is W.
And the final W. And the final
Oh, I don't have that, so I got confused.
So the I here is going to be the
I
I.
think you have the square.
Oh, there's a
No,
comma.
it's the W.
And then minus.
That's all. That's Peter square.
Would you just put in the
You saw that way. You got the wrong.
1/2 I omega initial squared
Over the direction.
plus that. So,
Well, I mean, this one's going that way.
And so.
so it's just energy. What energy do I start with? Is my objects, are they moving left, right, up, down? Is there any tangential velocity? Are these objects like
No.
at some, no, there's no 1/2 mv squareds. Why? These cylinders literally aren't moving anywhere. Translational. Are they moving up, down, a noticeable, like we're just going to say they're not. I'm just going to straight up tell you they're not really moving up, down. Any springs?
No.
Are they spinning?
Yeah.
If you're spinning, what type of energy do I have? And how many objects do I have? They each have, there's 2 objects and they're both spinning. So that's what I start with. 2 objects that are spinning. Great. And then I end. Same thing. It's not moving left, right, up, down. It hasn't really changed its Y position. I know the picture kind of looks like it does. We're going to pretend like it doesn't. So at the end, what energy do I end with? I just end with rotational. Just plug in the numbers and solve. And reminder, I final. How do we find the final I? You just add them together like before. If 2 objects get stuck together, what's their total mass? Add them together. If you have 2 spinning objects stuck together, what's their total I? Just add them together. So it's just 1/2 times 2 times 5 squared plus 1/2 times 1. Now, technically this W is negative, but what's negative 8 squared? Here, in fact, I'm going to write it here. If you square negative, does it matter? Turns to a positive, right? We don't care. Like, kinetic energy can't be negative because there's a squared term. 1/2 times 2 plus 1 times 2/3 squared. Yeah, you just solve for W. So, yeah, this is putting the ideas together. And then there's one last problem we're going to do, y'all. And that'll be the last problem, new-ish problem. So I'll do more review on Thursday. I probably won't start any review today. I'll just kind of give you all a blurb of what I recommend doing.
I've gotten some questions about why there's no translational. What's happening is this and not, it's not rolling. It's not this, it's just sat somewhere spinning.
Yeah. So V here corresponds to whether it's moving left, right, up. Is it X position, Y position, or Z position changing? If you spin a wheel and it doesn't go left, right, up, down, it's V is 0. And that's a
The velocity of the edge of the wheel is not necessarily the same as the velocity of the whole wheel.
Now, if you put that wheel on the ground, it will start rolling. And then it'll have a velocity.
I don't know if you said it earlier. Do you know when you'll finish the final exam practice?
My goal is by tomorrow.
Okay.
Yeah, my goal is by tomorrow. But rule of thumb, don't let that be your only study resource. I highly recommend you all only do that practice exam after you've done both of my quizzes, after you've done some of the problem sets for this stuff. There's only one practice exam. Once you do that practice exam, it tends to not be as useful. The more times you do the practice exam, the less it gets useful. So I highly recommend you all use that practice exam as the last thing that you all do once you've done all the prep work as a final. They're like, oh, it's great. It's all here. This is the only thing I need. Don't fall into that trap.
Will the practice exam be the same amount of questions as the final? So we could
Yep.
give ourselves 3 hours.
Yeah, the practice exam will be the same amount of questions as the final. For the same reasons that it matches. Yeah, no, it's a great question. All right. Last problem. And this is, it's number 18, a moment of inertia, because it's got it's not terrible, it's just got the most pieces to it. 3 children are riding on a merry-go-round that is 100 kilograms and has a 1.6 meter radius and spinning at 20 RPM. The children have masses of 22, 28, and 33. If the child who has a mass of 28 moves to the center, what's my new angular velocity? And it says in RPMs, but I'll quickly give you all the answer in radians per second. Oh, and I didn't specify this here. This merry-go-round is a disc. Solid disc. And I'll convert revolutions per minute to radians per second. So draw a picture of it. How many objects do I start with? How many objects do I kind of end with? It's going to seem a little funky. For now, that's the technique I'm going to mention. How many objects do you start with? How many objects do you end with? So, yeah. Already, how many objects do you start with? Plus them. Yep, I want the size, yeah. There's a disc plus the 3 kids.
I feel like you could then do what I was, that's what I was like trying to figure out. Do we, does it give us the discs are?
One after one square.
It does give us the.
Yeah, for a solid disc. We could do that. What's it going to be for the kids? So the key here is we can think of this as like if they're rotating about their center. So this is more like if we each this kid like a dot on the thing that's spinning. So drawing a picture here is going to help you identify what objects we have and how many you have and a bunch of things. Here's my disc. I'm going to look at the disc from above because it's so much easier to draw it. There's a disc. What else should I put on this disc? 3 dots. Where? These 3 dots represent the children. Where are these children located? On the edges. I don't care where on the edges. It doesn't matter. You could put one here. You could put one here. You could put. It doesn't matter where, as long as they're on the edge. Because fun fact, when they spin a little bit later, they're going to move to somewhere else anyway. Doesn't matter how evenly they're spaced. We don't care about balancing this thing. Put them all right next to each other. Put them all spread apart. Doesn't matter. So that's my original picture. Now I want you all to try to draw the final picture too. There's still a disc. Funny, this problem mathematically is much easier to solve than yours. It's way better than the momentum example of the three deer sitting on a thing and you jump off it.
Yeah, exactly, but then I couldn't figure that out either.
Arcane is an angular velocity.
All right, so my final picture, where my kids be? Same spots, one's in the middle. Which one do you want to be in the middle? Does it matter? Oh, actually, it does matter, one of them. If we call this kid 1, kid 2, kid 3, kid 1, kid 2, kid 3, we do have to be careful because they have different masses. So, yeah, we're going to put kid 2 because he's just in the order that they're listed in the problem. Great. All right. So we're solving for angular velocity. You have an object that's spinning where things shift around. This is an indication that it's going to be a conservation of angular momentum. How do you know it's conservation of angular momentum? You have something spinning and things either shift around or two spinning things get stuck together. That's how you know it's a conservation of angular momentum. Things shift around or get stuck together. Okay? So it's conservation of angular momentum. I initial equals I final. How many objects do I start with? Yeah, so this is going to be the funny thing. If you tell me it's one object or you tell me it's 4, they're both going to kind of work. I'm going to do it as the 4 objects, though, because I think that's a little easier to explain. And then I will show you why you can... We're going to treat it as 4 objects. So how many I's do I start with? 4 of them. I1 initial plus I2 initial plus I3 initial. And then I'm going to call the last one disk. Just to keep them separate, I'm going to call the disk D instead of 4. I think it makes it easier to keep track of. Do whatever you want. How many objects do I have? Some way go in the opposite direction. We'd have to care about that. All right. At the end, how many objects do I have? We're going to do the same thing. 4 objects. I1 final plus I2 final plus I3 final plus I disk final. All right. What do I replace my I's with? What's the equation for... Oh, I've been putting I's. This is wrong. L's. These have been the wrong letters the entire time. Reminder, remember y'all I's moment of inertia, we're doing L's for momentum. L. It's easy to mix them up, but man, if you'd put a bunch of I's here, that got really bad for us if we'd actually plug those in. Alright, great. How do I solve for L? Remember, it's like regular, if it was P, it'd be M times V. If it's L, it's... U, yeah. IW, right? So I1, W1 initial, plus I2, W2 initial, plus I3, W3 initial, plus I disk, W disk initial, equals. And you're like, oh my gosh, this is terrible. Just wait, it's going to be so much nicer. If you all can already see why it's nicer, that's awesome. If not, look at this equation and you think about it a little bit. I2, W2 final, I3, W3 final, plus I disk, W disk final. You're like, oh my gosh, that's all, it's so, Don't worry, it's going to get so much nicer. Let's look at one thing at a time. We're looking at the I's. Let's look at the I's. For the kids, what object are we treating them as? Point masses. They're little dots on the circle. If you draw them correctly, it makes it easy to see that. So I1, 2, 3, that's just going to be mr squared. Now, you got to use the right m, you got to use the right r. Great. They have different masses, so be careful. Great. What about the disk? What's the equation for the disk, if anyone found that? 1/2 mr squared. Great. So we know our i's. Yay. We next look and we see those w's. Oh my gosh, 4 initial w's. Do I give you 4 different w's in the beginning?
No.
So that gives us an indication that there is something going on here that we need to recognize. How do the angular velocities compare? So remember, angular velocity is how much angle I pass in a certain amount of time. Let's say it takes person 3 2 seconds to make a full circle. How long does it take person 1 to make a full circle? 2 seconds. What about person 2? How long does it take them to make a full circle? How long does it take the disk to make a full circle? If you have a bunch of objects stuck together, their W's are all the same. Because they're all making the same circle the same amount of time. Remember here, W is how fast you're spinning. They're all spinning the same rate. They all make a circle in the same amount of time. So the thing that's really wonderful about this, I1, I2, I3, iDisk, they all have the same W. The W is the same for all of them because they're all stuck together. However fast the disk spinning is how fast literally every single object on that disk is spinning. Thank you. What about the faster? Is anyone in this like making a circle quicker than anything else? They're all the same again. They're all attached to the same disk. No one's running backwards. No one's like hopped off the thing. So at the end, the same exact thing is true. Now, there is something I didn't quite write here. How does the radius of object... So, does the radius of my disk change? No. Does the distance that person 1 change it? Does person 1 move closer to the center or farther from the center? No. What about person 3? What about person 2?
Yeah.
Something that's a little subtle. You all need to put a little initial next to this I3 and a final next to this I3 because it changes. Person 2's I changes because they literally move. And because they move towards the center, if we just think about the concept, it's easier to spin the whole system because more mass is closer to the center. So, anywho. If you all see the answer, it's a higher RPM. This is what I told you all. If you're on a playground and you move to the center, you will spin faster. I can promise you. Try it for yourself. You won't feel like you're going faster, but your spinning rate will be faster. Anywho, now let's just plug in numbers. See if y'all can get the answer. This is all we're doing for the rest of the classes. I guess to make things opened up for you all, let me give a quick blurb on, so I'll do my final thing of talking, and then the rest of the class, you all can just kind of finish this up or ask questions, so I can be done with chatting. Preparing for the final. So this is my quick blurb of how should you prepare for the final. I've already mentioned this a bunch of times. Practice problems. So what I highly recommend you all do, go through old quizzes. Go through the old tests. Go through, I say the old tests. Maybe hold off on go through the old quizzes, go through the old problem sets. And another strategy I want to mention that I've worked with a few people now, and I kind of realized this. The formula sheet is a great, I don't know if I want to call it, the formula sheet is literally a summary of almost like all the concepts I've covered. Each of these equations represents a concept. Math is a language. So this right here, energy initial plus work equals energy final, this is conservation of energy written in a really tight space. Here we have conservation of momentum. Or did I actually put that on here? No, it's not. It's kind of sorted here, but not really. That one's not good, but sum of momentum initial equals sum of momentum final. Anyway, what I'm mentioning here, this is a great way, a great resource. Look through this formula sheet. If there is an equation on here that you don't know what it's used for, that's a flag that you should figure out some problems that it's used for. Because if you don't know what type of problems this equation is going to be used for, the inverse will be true. If you have a problem that uses that formula, you're not going to know to use it. So, a great way to study is to look through this formula sheet, and if there's any equations where you're like, I don't know what type of problem I'd use this for, try to find some. Go through the problem sets, go through the quizzes, because the inverse will be true. If I give you that uses this equation right here, and you have no idea that this equation is the right one to even use for it, obviously you're not going to know how to do the problem. That's a common thing I've seen. That's a really great way to kind of ensure you know what's going on. You all have learned okay, there's one exception down here. I need to delete this one. We're not doing this. And you honestly can delete this one. So these two down here you can ignore, but the rest of these above it are all good. So yeah, there's that. And I already mentioned this to you all. I'm going to post the practice test probably tomorrow. If that is the only resource you use to study, that only works if you know what you're already doing. If you're only using you should only look at the practice test after you've looked through the old quizzes, after you've done the new quizzes, after you've done your kind of studying, do the practice test last. If you do it first, you're going to end up with maybe a false sense of confidence because you're going to probably end up doing the practice test several times. And sure, the 5th time you've done the same problem, of course you're going to know how to do that problem. The problem is on the test, you're not going to have done those problems 5 times before. So you want to approach the practice test the way the real test is, because I only have one example of that. Use the practice test as a mock test. And the thing with mock tests is you can really only do them one time to actually match the real test. Because the first time you see the practice test will be like the first time you all see the real test. So if you want to make them as matching as possible, wait till the end to do that. And time yourself when you all do the practice test at some point. You all will have 2 hours and 50 minutes, which is a lot of time. In my opinion, more than enough time. But that's going to be based upon how comfortable you are, how quick you can realize these things. All that jazz. So, anyhow, that's my final blurb. Any last questions for me as far as studying and stuff? Thursday we'll do a review. I'll be here Thursday. That'll be literally our last class. I'm going to go not PowerPoints. I'm going to go through the old stuff, make up some problems for rotation, make up some random problems from previously. It'll look like all our other reviews, just everything. It's going to be, a lot. Okay, so if you haven't finished all this one, try it out. I'll be here till the end of class. As always, y'all can leave and go whenever you want. That's never changes. Yeah, and I'll solve this thing out in a little bit as well. If you haven't grabbed a note card, they're up here. If you're online, I'll have them in my office hours. I'll also have them Thursday. You are allowed a 5x8 note card in the final, just like a 5x8 note card in the other exams, but this has to fit everything that you might want. Sure. No, I was at some point I have to solve this.
This question, Revolution does in it.
Yeah,
I got
Yeah,
the
it just
answer,
has
but I was thinking to change it to radio.
Because the radius is
So this is that's up to you.
Oh, either way. Okay.
So
The I.
yeah.
Okay.
His radius, he's spinning in the same. It's like spinning in place.
Yeah.
Okay, good.
There's no momentum to it.
Oh, no, you
It's
just.
just
No, you're good.
Wait, no. This is the
Yeah, that's good. That
Yeah,
was.
I got the right answer.
That was good. I think I divided by 2. Something weird. I think the final answer here is way off. Does this match yours? 0.067?
Mine. Wait.
Yeah, I think. Let me.
Mine, like the answer, I got 25.28.
Yeah. But in radians per second, what did you get? Because I think
In radians per second, I got 2.6.
2.6.
Yeah.
All right, that's probably more right than mine was.
Meters per second.
I wouldn't pick my word, but.
I'll double check in a second.
On the daily exam, do you
Well,
It's only like a couple minutes or something. Yeah, it's just passing out the exams is really the only thing, and that's super quick. Yeah, go for it.
See, that's what I was trying to ask.
Revolutions per minute, and it's 2.5 per revolution. Yeah, is that better? Is the final radians per second better?
Yeah.
Okay. Yeah, I divided by 2 pi instead of multiplying by 2 pi. What's up?
just want to double check the lowest two fifth grade.
I did it wrong and retried it in
One.
RPM.
Okay, just want to check.
Yeah, and it should already be, I think, on my end I can see which one that is, but maybe on your end it's marked as well. I don't know what it shows you on there.
Okay, I think if I put in my text lab, I put it within, it'll tell me, but I think his.
Yeah, most ones drop. Yeah, same with labs.
Second to last is
Oh yeah, and I'll still have office hours next week as well.
Same exact times.
Yeah, I'm debating maybe making them a little longer. I might make them a little longer in like a couple of the days, just to give more opportunities. And also, we don't have class, so.
We don't have class on Tuesday, so like, well, or not.
I understand that. They all have the same. Because it's a Yeah, wow. They gave us a study week last semester.
Did they really? I don't know. Oh, no, there was Thanksgiving break. No, literally, Monday is the last day of classes. Yeah, so we have classes Thursday, then we're done with classes, and then the exam will be next Thursday. Yeah, as decided by UCF.
My question was the first question on the quiz. Because I remember that I was having trouble with it, but I can't access it, so I don't really know what.
You can't access it, really?
Well, I mean, I can, but I'd have to like I can't see like what I put for the answer like that.
What?
Without starting it again.
Let me check that. Let me finish this problem real quick, and then I'll check
At least
that.
not on my phone.
You should be able to.
I probably put it on my computer or my iPhone, but it
Okay.
won't let me see it on my phone.
Okay, I can pull it up in just a second. Let me finish this, and then I can close the stream.
So you could do what it seems like you're trying to do is L for F equals. Seems like you're trying to do this. Is that right? And then find each of them individually?
Yeah,
Okay.
that's the easier way.
Yes. So you could do instead. they're all just sat on the same disk, right? So, are any of them moving relative to the merry-go-round? Spinning at the same angle. So that means
they all have the same, yeah.
Okay, so wrote out all the M1 R squareds for each kid. So M1 R squared plus M2 R squared plus M3 R squared plus 1/2 M disk R squared, because that's moment of inertia for a disk. And then the right side's the same thing, but the second person has a radius of 0 because they are at center. They move to the center, so that's the only thing that changes. Plug in the numbers, solve for a mega final, and that's the end.